the benefit of the recording, we're now going to continue on from the early stage stuff that we did last week. In essence, all we'd really done is we'd looked at taking them nodes, and then we generated, as some have nicknamed, a linker model for a truss. And the linker idea is simple. Along your geometry, all you've actually got is node, node, element in a single configuration. Then from there, what you do is you assign your second moment of area to be tubular, to box section, and then you can actually simulate what's around it. Now, what we'd never done is we didn't expand that further into a three-dimensional state. And that's what today's session is really about, expanding it and looking at meshing and just being sensible with the mesh and just thinking about what will get us the best type of result that we're looking for. A lot of this will come down to your own experience. You can't go in totally blind into FEA and then just expect an ideal result. You must have a rough idea as to what this thing's going to do. Just to give you an indicator of the type of thing that you'd be best looking at. Now, the example I found was Marin mountain bikes. In the 90s, they were a huge company. They were doing incredibly well. And I don't actually know what happened to them, but what they wanted to do is look to expand, and they were looking to expand to road bikes. And they played around with the different ideas for materials. Now they approached ANSYS, and they actually said to ANSYS, what we want to do is we want to be able to look at different variants of materials for our bikes, but what we'd like to be able to do is to minimize the cost on prototyping. So what we're going to do is we would like to simulate different materials being used on the bike, and then we'd like to look at the type of responses that it got. Now, they tasked their, well, I don't even think it was called ANSYS originally, but they tasked the company with going away and coming up with an idea to make it work. And how were they going to make it work? So what they essentially did is, they took the road bike. Now, for just to give insight to people, let me just find a good example. So your typical road bike. Now, I'm just looking for the more older type, so it's more like this, where you've got these tubular sections all the way through. And what they wanted to do was to try and come up with a way to verify the material that was being used and then run to a more bigger example. So all they did is they said, right, what we'll do then is we'll take this section of the frame, we'll take the cross section, so this area here on the cross frame of the bike, and we'll simulate pulling that off and then calculating around its behavior and displacement. It seems dead straightforward. To calculate it is nice and straightforward, and in fact it's what we're going to do in just a second. But what they did is then built that in, and then they were able to start looking. Now what we're going to do is do the exact same thing. I've drummed up an example of how they did it and how it worked, and then what we'll do is make it. So in the nodes, these are the nodes. Now this is a basic thing. Now I spotted an error down here earlier, so I will show you where the error lies. In our example, what we want is we want a bar that's attached to the wall, a wall thickness of 2.5 millimeters, a length of 500 millimeters, and an outside diameter of 25 millimeters with a loading. Now the loading on it is just to give us something to operate to. We could change that, make it higher, make it lower, but look at exactly what it's doing. Now for our first sample piece, what we'll be using is, I'll put it on, structural steel. So it's 200 to the power of 9 Newton meters gigapascals with a Poisson's ratio of 0.3. So what we want to do is we want to calculate two things. We want to calculate the Young's modulus. We want to calculate the displacement by epsilon, and we also want to calculate the stress. I didn't put that out. That's a shame. Now I've worked it out here, but what we're going to do is do it anyway, because it's good to be able to go through that process, and I want to show you how I got to that result for anybody who is unsure. And so we'll calculate the displacement, and we'll also calculate the stress concentration. Then we're going to go into ANSYS and try and build this into ANSYS and look at the all-important meshing procedure and look at what type of a variant result it's given us and why is it doing it. Because again, this comes all the way back to the mesh. You can put a standard mesh on there and all the system will do is just apply what it thinks would be best. Doesn't do you any good, but what it will do is just apply what it thinks will be best. Now I'm told in 19.1 that adaptive method is even better, but we'll find out today. So what I will do first is, let me call up my Excel. So I'm going to open up Excel. So I've got my Excel here. And right, so from here what we need is we need to just take some variables from it. So we know we've got PL, Young's modulus, and moment of inertia. We know that we've got the outside and we've got the inside, so I'll go ID, well IR, oh god, ID and OD. Now what I'm just thinking about is just the open space and the inside space. So what I'll do is say, I'll go IR and I'm going to go OR. So inner radius for the space, given its 2.5 millimeter wall thickness, and we have an overall size of 25 millimeter as a diameter. We know that it's going to be 20 mil, so we know that the radius of that inner will be 10. And I'll do this right actually. I'm going to change it. This is just me being pedantic, but I'm just going to change this around and go OR and IR, just because I'm just being pedantic really. So I'll go 12.5 and we know that that is 10. So this is the inner radius for the space, and then the outer radius for the whole bar. Now this is purely because when we calculate that all-important moment of inertia, we need to know what the inside space is, so we can add all these together to give us a true representation. Now I'm only doing this as a reference. It's the only reason why I'm doing this. So I'm not using Excel for anything very specific, if you will. Let me just go. I'm going to put some comments on here as well, because what I'll do is I will add this onto the Teams site. So I'm just going to put in a comment. Brilliant. Why is that not allowing me to? I'm not going to mess around with that. I'm not going to mess around with that. What I'll do is now bring in P. I'm going to go L, E, I. Whoops. Now I'll show you where this is coming from. On the notes, we've gone load, length, Young's modulus, and moment of inertia. That's just the reason why I put it on there. So then it ties directly into the notes that we're talking about. So we want to get that all-important displacement, but we need the first things first. So for my P in this case is 100. So this is my load. the length excuse me, I'm burping like mad. The length is 500 millimeters. The because you'll notice here I'm in millimeters up here, so this will be put out in such a stead. Where our Young's modulus is 200 to the power of 9. So what I'll do is say 2e plus 11, 200 to the power of 9. And then finally I need my all important moment of inertia. So I'm going to do it 1 over 4. So that is basically pi r. And with that, we'll obviously take everything to the power of 4. So what I'll do first is go 1 over 4. Get this right. Let me get this right. I want to get this right first. So I'm going to go 1 over 4 multiplied by pi. Open arguments. Close arguments, because it's just pi and it's relative. Then I'm going to multiply by, now for moment of inertia, I obviously need my inner rad and, well, my outer rad and my inner rad, and then literally going to minus 1 from the other. So what we'll do is go outer rad, taking that to the power of 4, because I'm going by 4 for my overall equation. I'm going to minus minus inner rad over, again it's just because it's a pipe, so it's literally going back to high school days is this. And I'm going to put another set of brackets on the end so it encapsulates it in one single hit. Hang on a second, I think I had a question come through. Oh no I didn't, apologies. And then if we got that right, it should give us, oh my god, so this now gives us moment of inertia, Young's modulus, length, load, inner and outer rad. So I'm just going to put them into a little box. So now that I have these, yeah, I'm starting to think the same thing, Jordan. That's why I might take 5 minutes in a minute. Right, so what I'm going to do is just bring in that deflection. So this is my all important equation that I'm just going to do. Anybody who's confident with this, please just, you know, fire away. Don't wait for me to do it. So deflection. You don't have to use Excel as well. If you prefer to use something else to calculate these in, that you're more than welcome to do that as well. I'm just doing this just because it's one of them tools that everybody's seen and everybody's been able to navigate themselves around. So, and this is really, really, really straightforward to calculate my sigma. I'm going to go open brackets. Now I'm going over it. So because I'm going over it, I'm just putting it into a bracket because I want to make sure it's exactly like in schools at the moment. You see a lot of them doing this. So what I'm going to do is bring my P. Oh, that went well. Go equals open argument P multiplied by L all to the power of 3 divided by open brackets 3 multiplied by Young's modulus multiplied by my moment of inertia, and then if I've not missed any brackets off, I don't think I have, close that bracket out and then enter. So that suggests a very small amount of movement. very small amount of movement. But what we're going to do is map this. We're going to look to see if this is a genuine case. So if it's to the power of 6, it is coming back in meters. But we'll see. We'll see, because I'm not convinced. So let's go stress. Now these equations are the best in the world for things like this. So what we'll do now, it was here. In fact, I think I fixed it there. You still might have an error here. It might say something like M or something like that when it should actually be load. That was a typo. So I don't know if I think I fixed it, but I'll check it again today. That should be load, so that will be P in this case. So what I'll do is equals, really easy, straightforward. So I'll go open argument, and let me think. Right, yes, I was just thinking there is actually an extra piece to this. So I'm going to open argument, and I'm going to go P multiplied by L, or close that, and then go over I, A. That will give me just the cross-sectional area. And because it gives me just a cross-sectional area, what it actually does is it means I need to multiply it out by the length of it. What I actually need to do is I also need to now bring in my outer radius. So what I actually do here is I'm going to capture this in more arguments, and I'm going to multiply it by my outer radius. So that gives me 55.2 megapascals or pascals. And what we're going to do is we're going to pass this in, and we're going to take a look to see how well it maps against it, and we're going to see if we can get something realistic from it. But that's all I really wanted to do that for. Now if I bring this back and just look along the side, you'll notice here that that's where these values are coming from. Just so you know, I'm not bullshitting you as we've gone through. This is where and how I've actually pulled these values, just so you're aware, that's all. Okay. Right, so let's take a quick look back on. Let me just go back to the notes again. What I now want to actually do is I want to look back at that, and I now need to generate this in ANSYS. Now this is a three-dimensional body. Really, arguably, you could do the linker on this if you wished, but a benefit of what we're going to do is really look at what happens when the mesh doesn't function like you want it to, and how lethal it can be. So let me just close that. Got all these different windows open, apologies. So what I'll do is I'm going to come back out here and minimizing. To minimize also, because what I actually want to do is I want to open up Horizon, and if you've not done yet, please do open it. So I'm going to log in with my credentials as normal. On to 19.1. Apologies, 1 second, let me just close the door. Who needs a doorbell when you've got a dog? Right. We'll get that, we'll get that. Any minute now. going to freeze my my OneDrive just to see. Right, okay. I must admit I did not know that this one was coming up. Has anybody else had the same problem with it failing? Strange that it started to fail now. Just want to see what mine's going to do, because I'm not doing anything. Yeah, I was starting to think the same thing with that a lot of us were trying to access it all at the same time, and it could be emerging from that. What we'll just do is perhaps hold on for a moment just to give everybody a second chance to try and get onto this. It seems that if the portal is open and too many people access it at once, what it'll do is cancel people out. Yeah, I thought so. It's like as if only a certain amount of people can actually access it, and then it'll let them through in like a queue, or not even let them through, just throw them off until you start again. Seems an interesting one. Does that? It's a side effect which I didn't know existed on this type of system, but it very well might be that. Which is a little bit frustrating. Again, it's very frustrating, but it is what it is with this. We'll just have to try and work to that as much as we can. Again, I'll just give everybody a couple more minutes just to try and get everybody on. Two minutes. I'm just gonna nip and get me and get myself a Rene. So that gives me. So apologies for the pause there, but I just need to take a few minutes. Right. So we met this last week. This is the ANSYS interface. As we will have a bit of a navigate through all of our toolboxes that we can use that's built into ANSYS. This is ANSYS 19.1, so some of the solvers are the most relevant and up-to-date solvers. Anybody who has seen ANSYS 20 or 22, I can't remember which one it is. The only thing that's changed on this is the interface to it. The meshing procedures are still, to this day, very much restricted and still not the best. Well, no, I say not the best, but they've still got these predominant errors from the start in it. And what people are trying to do is minimize that error. So what I'm going to do is drag and drop static structural. Because again, in this example, what it is we're taking a bar and then we're just going to place a stress on it. So I'm going to left click, drag and drop static structural. So drop. So purely left click, drag and drop into the little box. Then the flow chart will appear. Now the one thing that we didn't really take an examination into last week was the engineering data. just to make sure that our calculation is on the right value. So we chose a Young's modulus of 200 to the power of 11. So 2 to the power of 11, so 200 to the power of 9. What I'll quickly do is just right click and I'm going to go edit. This allows me to see the material that's in this simulation. I'm not going to go to the library as of yet because I don't need any more data, but what I can do is just check down. We see there that we're at 2e to the power of 11, and here we are again 2e to the power of 11. So we're on the right Young's modulus track. We're using the correct data for structural steel. Again, if we choose to make the bar out of something else, or if we look at a variation of a different material, we need to just map everything that we want against it just to make sure that we're getting something realistic. So what I'll do is minimize that, and now anybody who's CAD savvy, again, this is not a CAD exercise and will not be a CAD exercise, but if you are CAD savvy and you are keen to bring in your own geometries and to test your ability as a CAD designer, this will test it. If your models come in with errors, then you need practice, and it is black and white to that. Any types of inaccuracies in the design, the translation across can be brutal. But what we're going to do is we're actually going to model this from inside of here. Now, the only reason I don't use Space Claim is I've not really used it. It is ANSYS' newer version of a geometry maker, so it's a bit of a CAD system. It's not like CAD like you'd imagine it, where you can build assemblies and really look as aggressively at the overall picture. All it is it's to make a single part or single geometries. A lot of people have had a lot of luck with using Space Claim, but again, I've not really looked at it just because I prefer CAD outside of here. But what we're going to do is use the new design modeler geometry. Again, if anybody wants to import from CAD, there's your options there. You go to browse, find your part, but what I'm going to do is go new design modeler. Let's see if it opens without crashing, which would always be very nice. Again, not the most attractive looking thing in the world, but can do an awful lot of good. So we know that we've got 25mm diameter. We know that we've got a 20mm inner diameter, and we know we have an extrusion of 500mm. The geometry on this is not too tricky to do, but what I'm going to do, again, for those of you who are savvy in this and comfortable in doing this, please do fire away and sit back. But for those of you who are a bit unsure and still a bit nervous, I'm going to go dead steady with this, dead straightforward. So always think of your triad, and you look here. Again, I know I did this last week, but I'd like to be consistent. So if you look at YZ, YZ plane tells me that it will be operating on the downwards. XZ tells me that it will be operating on this component here. Oh, XZ, which is here. And then we've got XY, where it will be operating in our XY component here. Now, for the nature of what we're doing, it's a pipe. Let's not overcomplicate it. So what I'm going to do is click onto XY, sorry. Come down to modeling. Navigate next to it, and you will find sketch. So what I want to do is I want to look at the plane. Easiest way, right click, scroll down, look at, left click, and we've now got our panned view. So then navigate back across. I'm doing two circles, circle, and I bring my cursor around, and you can see it tracking to the axes. Now, I know we did this last week, but I do want to still be consistent with this. So I'm going to track along, and then you'll see mine snaps like that. That's to the center. I don't really like the way that it does that, but hey, I don't build CAD. I mean, I don't build ANSYS. So what I'll do is left click once, drag my circle out, bring my cursor back in, left click once again, and left click again to finish it. So that's me clicking and not holding or dragging anything like that. So some of you who've done CAD will know that you can normally left click, drag it, and then just let go and it releases it. This is a bit more primitive than that. So I'll bring that out and I'm just going to put it like that. So I've now got my two important geometries, or not geometries, profile sketches. And what I need to do is I need to dimension these. So I've got dimension. I really hate how it just says D1 and D2. I like it to give me the numbers. So if I come down to display, I can go name and value, or just go value. It's always defaulted to name, and you think, why would you do that? The other thing is I've just thought. Other thing is it's always important to check the units that you're going to operate in. It's going to come back to this. We know that all this was defined in millimeters. So what I'll do is go up to my units, and it's set to meters. I want to change that to millimeters, because when it's set to meters, it will not, no matter what you do, allow you to defer at all. So, you know, like in a lot of CAD systems now, if you were working in millimeters and somebody gave you a size in inches and you thought, I cannot be asked to convert it, you can actually type it in inch and then the CAD system will convert it for you. Believe me, not in this. So you need to be consistent as to what you're operating with it. So what I'll do here is I'm going to go to General. Now this, for anybody who, again, I always refer to CAD because it is the best relation between the two. For anybody who's again, used a lot of CAD, you'll know that you have auto or smart dimension. In the smart dimension function, that's what this really is. It's just saying, click on it and I will give you a dimension. So I'll click on the first one. Then I'm going to click on the second one. And if you look here, it's a lot bigger than what we were hoping it would be. So I know my first size for the outside is going to be 25. I know for the second size, which is my inside, was going to be 20. Just to confirm, 25 and 20. Don't forget, if you look at the reference to the dimension, it is diameter, not radius. And it's a bit far away, so I'm going to zoom in. I'm going to right click, keep my finger on the right click and drag a little box over and then let go of my right click. Do it again and again. And that gives me my size here. Another thing that's annoying, which you'll just have to get used to it. If I scroll this back out, you look at it, you see how I'm trying to make, you go, what? Right. You cannot move the, I'm messing things up here. You cannot move the diameters unless you specifically say it, the dimension, sorry, unless you actually modify the dimension. It's a real pain in the backside, but for what I want to do, for what we want to do, we just want to make sure the dimension's right. We're not producing drawings from this. This is just going to give us the all-important piece of geometry that we need. Now, let's push it back out. So I've now got my geometry, and what I want to do now is extrude. So I can go back out to here, or I can stay in there, it doesn't matter. Come to the top. Now I've got these turned on, some of you might not, so what I'll do is go about it the normal way. So if I come up to, where is it? There we go, under create, I've got extrude. You can see how long it's been since I've used it then, just because I couldn't remember where that was, that's why I put them down there. And what it says here is the geometry. What geometry do you want to extrude? Now the sketch is already in there. It already knows that I want to do the sketch. I'm going to apply it to that extrude, to sketch 1, which is already done. Then it says, what operation do you want to do? Do you want to freeze it or add material? Now, a freezing process, what it does is it holds the geometry in space. It's not really something that you can modify or change with it, but it allows you to model things like air or gaps or things like that. But we're not going to do that. All we're going to do here is come down to our depth and change this to 500. And then I'll go to generate. Generate is, yeah, it is just what it is. So we'll hit generate, and what it'll do now is make me my geometry. Has anybody struggled to get the geometry made, or at least drawn? Excellent. So, going through this now, if I extend on my extrude, we've got our sketch there, we've got our extrude there, everything's on here. Once this is done, what the system does then is it categorizes it and turns it into a solid part. This is a big indicator. These are really, really useful. Now for this, we just made it. However, if you wanted to test to see if you'd done any geometry which was well translatable, when you import it to ANSYS, it will give you either solids or surfaces. If you've done anything a bit shoddy in your design when you import it, ANSYS won't be able to resolve it, and it will turn what could be a basic part into 50, 60,000 surfaces, because some of the surfaces will not be resolved and it will be left open. There's ways of patching that, there's ways of fixing that, but that gives you a big insight. You notice here it's even brought in a new CAD importer. So under your CAD importer, you've got all types of different things you can try and make it work better, but it's one of them things that a lot of people have tried to do for many years to try and get it working nicely. So that's the geometry that we need. So I'm going to close that. Feels weird to close it because you kind of think I need to save it. Don't forget, this is my project window. Within my project window, what I want to do is to be able to make sure that everything's stored at the same spot. So all I do now is hit save project as, and it will take me to my uClan saved area. So this is my uClan account that you can see on the screen. So I'll just call this is point verification. What it'll do is it will save the geometry and then save multiple little files to go with it. If you do intend to share these and actually pass data backwards and forwards, don't just email the simulated folder. If you email just a simulated folder, it's missing all the sister folders. If it misses all the sister folders, it just comes up and goes, I have no idea what you're trying to do, totally pointless, and it will just fob you off. So you're always better off, well, you're much better putting these into a library or a little box. And a little folder, sorry, not a little box. But you're often best doing it that way, just to give yourself that bit more security. So, I tell you what, we'll come back to that. I keep wondering whether we should bring in a second material to actually test against. But we'll stay with our original verification, make sure this is right, and then let's move in. So I'm going to left click on the model, and I'm going to double click. Now all it does, grabs the engineering data, grabs the geometry that we've just done, grabs the code that it needs to know what it's going to do. So in this case, static structural, then formulates the space, then formulates the material, assigns the Young's modulus, and then gives it its first initial step to getting itself set up. So hence we have geometry, we have materials. So if I extend materials, we know we're using structural steel. Our structural steel values we can find here. I always like to look through the engineering data personally, but either way. Now if I come to here, go onto my geometry, gives me the insight about the geometry, tells me all types of different things, the geometry, the length, the rad of it, the overall package of it. If I go into the solid itself, it tells me that the stiffness behavior is set to flexible. I could set it to rigid or a gasket type behavior if I wish, but we're going to bend it. If it's not flexible, it's not going to be doing much. Again, the active, like I know that the active material in this case is the structural steel because it has a green tick attached to it. So if I come back to the solid, I look onto material, you can see a sign there is structural steel. Now, if we get chance, if we get time, we're going to come back to bringing in different materials. But first things first, I want to set this up just because there is some really key things where you come away and go, oh my God. I mean, when I first started doing this, I came away and thought, oh my God, I never realized that. So when we come down, we've got the global coordinate system. See how this is measured here? If you have something that you're trying to emulate a behavior, so for example, let's say you've got a linear actuator that is essentially used for landing gears, or you've got it used for any type of mechanical system, a large lifting system, but you want to keep that computational element low, want to keep it down. What you can actually do is add further ones in here, and you can say that global system is moving in this direction. And all it'll do is it will just concentrate on your geometry. It's just a sneaky way of keeping things minimalized when it comes to computational elements. So I'll come on to mesh, and I know I've said to you all from the start, you can't just hit default. We are going to hit default. What I'll do here is I'm just going to click, well, I'll right click on here, got all these options. It's never clear what they all mean, but I'm going to try and help to show you some of these things. So I'm just going to go generate mesh. Oh no, that's a swine. That is the automatic adapter. Oh, that is a swine. It's actually done a good job. Just out of curiosity, has everybody else got the same mesh similar to me? Because I'm not sure whether it's just a setting that I've set up before and I've forgotten to switch it back. Okay, yeah, okay. Now this is the result of ANSYS's, yeah, okay. This is the result of ANSYS's new adaptive method. Bloody frustrating because it's going to make me look like a silly sod. What I might do is I might manually change this round just to give you a bit more of an insight as to what it is that I... Oh, wrong button. What it is that I've been trying to do. Oh, I've got all these buttons up here. What's that one? Oh, yeah, okay. So, 1 minute. Not there, not there. Resolution 2 seconds. I'm just wanting to just double check and make sure that I've got basically what is very common meshing procedure that's already on here. It's such a pain in the arse, this. 1 second. And what I'm going to do is I'm going to change this, but then I'm going to change it back. this is very annoying. No, it has. It's still done such a good job. Swine. Okay, now frustratingly, it's actually done a quality mesh from the start. To be honest, ANSYS is notorious for being very good at actually being able to do these things. But the trouble is it's now shown me as a bit of an idiot because it's actually made me a mesh, which is very acceptable. Let me just see if I can bring this back. Oh, let me go linear. Now what I'm actually doing is just trying to remove the automatic function. No, it's still doing such a great job. I'm actually trying to get this to trip up, which is lethal really, because this company are very good at what they do. Right, okay. Then I'm not going to waste too much time with this, but so I'm going to have to try and explain this a little bit more manually, if you will. Bit annoying, but what we'll do is let me just build that back up. So what it's actually done is it's used a combination of tetrahedron and quadrilateral type mesh. Now you notice here it's in like a brick fashion. This type of mesh is exactly the type of mesh that it needs to be if you think about it. Now when we bend this, what it's going to do is it's going to deflect around Y. And what we want it to do is we want that stress to concentrate. Now, often what can be brought in, it can be a triangular type design on it. Now, I did have a cracking example of this that I was going to bring up. Let me just see if I can find the damn thing. Yes, I do. 2 seconds. Now, I prepared this. Here's one I prepared earlier. But I prepared this just because I wanted you to see exactly what can be very common in these systems. So I am going to have to just do it. Let me get rid of that. Damn it, even that's not worked. Trying to trip ANSYS up, but it's only because you guys do really need to see what a bad mesh would look like. Now, sadly I'm having to pull straight from the notes. But if you see here, we have these triangulated structures here. Now the tetrahedral type approach like this is good, but however, because this thing is going to bend in the way it's going to bend, this type of approach is not really the best way to address it. The better way to address this is what ANSYS has actually done naturally, which is to build these approaches where the nodes, because don't forget where these, it's a bit laggy, is that? Where these elements meet, there are dots, there are nodes that's on it. Can I actually see these nodes? I might be able to see them. Nodes. So you see where I can select there. And what it's actually done is built the ideal mesh for it, which is really annoying me because I do like to show you guys that what can happen if you do use a standard mesh, which is a bit shoddy. Sadly, it's doing a good job, but what we're going to do is build onto it and try and take a bit more of an in-depth look as to what it's doing. So, I'm going to go into my static structural and go insert, and I'm going to go fixed support. Now what I'm going to do is just zoom into my lower side here. On my fixed support, this is obviously where it's going to be connected to the wall. Now, every year I've had lots of students who have fixed it and also tried to apply a force on the same spot. Then they come back and go, ANSYS is well crap, it doesn't work. No, it's just you've tried to move an immovable object. So I click, come on. Oh, it's because I need to be on my face selection. Click onto the face, come over to apply. If I've done it right, it will turn purple or blue. I've had students argue with me for years that it is blue. For me, it looks very purple, does that? But anyway, so I'm going to flip that round and I'm going to come back across and I'm going to change this. So I'm going to go static structural. I'm going to right click, I'm going to go insert, and I'm going to apply a force. Again, on the end face, click apply. Vectors. Vectors will make it normal to face. It's normally what it is, just a normal to face. Or you can choose a direction. You can click on direction. You go, oh yeah, it's good, isn't it, that? But it's only normal to the face. I don't want that. I always prefer component. Component's easier. I prefer it because you kind of look and go, right, it's going 100 newtons in this direction. Happy days. So in my Y component, all I do is because I'm relative to the triad, I know that I'm going to act downwards. So let me just spin this around a little bit. I want to act downwards. So I want to act that direction. Wow, it even now gives you an indicator. So you notice that my cursor at the bottom is even telling me that's a minus Y. So in other words, let's make that minus 100. I just want to zoom this to fit. Zoom to fit. And if I've done it right, it will be red. It won't tell. It won't give me an arrow. So anybody. Oh, now it gives me an arrow. And it will just give you an idea of which way it's moving. So go zoom to fit. And now we've got structural steel. We have mapped against our exact examples. So let's bring this back. Our exact example, which sits here. And what we can now do is come back and model this a little bit further. We've got everything sitting in, and what I actually want from this now is I want to take, I'm going to insert, I'm going to go stress, I'm going to go for Miser stress, and I'm going to right click, insert, and I'm going to go deflection, and we'll go total deflection. They're the two elements that we've calculated out, and hang on a second, let me get myself all mixed up with all these different buttons going on here. So yeah, we're now gonna just come in and let's hit solve. Shouldn't take 2 minutes because it's not a very complicated geometry. The mesh is still turned on, so what I'll do, for me, I'm just going to go no frame. I prefer it like that to give me an idea of the deflection. Units appears to still be in meters. Units, so I'm going to go on metric in millimeters. So we are 1.8. And I have 1.8. 1.84 actually, so we're pretty much there on the ball with that. Now to map against what we're getting for the deflection. Now you look here, I'm glad it's not giving it perfectly, so at least we've got something that we can examine with this. So if you remember last week, ANSYS, what ANSYS will do, ANSYS will say that we don't know everything. What we're saying is that your error on your maximum value is between 53 and 59 megapascals. And to see if we are in the right ballpark, what we can do is go to 59. Well, we've got 55.2 megapascals, and there confirms that we are right. So ANSYS is doing the job, but then you do come away and go, okay, how much further do we really need to move? How much further do we really need to move with this? It would be ideal to just try and tidy up even more, but this is at a point when it comes to meshing. This is at a point where you need to decide where is your cutoff point. how much more space do you need, and how much more development do you need to do? How much error are you willing to accept? Don't get me wrong, if you go into a meeting and you say to somebody, right, I've got 67% error between my simulation and my actual calculated results, people will go, wow, you need to tidy something up there because something is horribly wrong. But I mean, given the error percentage between what we're getting here, because we're in that band, so we are in that right figure, what we would like to do is try to see if we could tidy that up that little bit more, and in an attempt to try and bring that closer. Now, I'm not too fussed with the deflection. What I'm actually really fussed with is more of the megapascals that it's providing. Where could this be coming from? I'll switch back on my mesh. Oh, that's a ghost. Short mesh. So as we come in, I'm just going to zoom it to the particular areas. When you look there, you can instantly see where this mesh comes from and how it's actually refining itself. It's refining itself to these particular areas. But you look, it means that them 4 nodes that you can see that's in a triangle, in a box type shape, and the 2 nodes connect to the actual target, and also that node that is connected over here. These are the key nodes that are reporting the maximum tensile stress. However, the compressive stress, whoops, and then lower beneath we get the same thing again. It's really laggy, is that? And then we see here that we've got the compressive stress that's occurring around here, which is not massive, as you'd imagine. It's all going to be in the ability of this thing being able to hold itself in place. So what I'm going to do is go back to my mesh and see if I can just offer a bit further refinement in that. There's a few things you could do. I mean, the most common one is people saying, right, well, let's just make the mesh super fine. You could do that, easily do that. So if you look here where I've got sizing and I've got default resolution, I can put a bigger resolution onto it. Where I've got spanning angle, is that, oh, well, see, well, what I've been doing, Stuart, just to feed you, that's why I record this as well, just so that if you do get any specific freezing, and I've been making sure that my microphone's running, but if you do get any specific freezing and you're unsure, you should be able to bring it back. So I don't record this online. I record this to my hard drive just for that reason, because I think it's lethal trying to teach online and having blocky or it moments. So yeah, apologies if that's happening. This week my MS Teams has been shite, to be honest. It's just been awful. So all I can say with that is I'm extremely sorry about that. But if you do hit any more issues of going through, please do let me know. But I am doing my best to try and get that sorted out, because for some reason it just fell out with me this week, big time. So what I'll do is just jump up my resolution. I've gone to 0.3 resolution. So what I'll do is update again, just to show you what it does. And you go, yeah, not done much. Now, the idea of adaptive mesh. Now, I did this yesterday, actually. It worked really well, but let's see. I'll just say adaptive. Well, it's still there. The idea of adaptive mesh is what the system can do is add nodes onto elements, and it'll subdivide itself again and again and again, and add more and more nodes on and off. So let me find a good image of this to give you an idea. Oh, this one is what I used yesterday. So if we scroll that in, right, so that's your very basic node approach, where they're equally spread across. Now what you can do is you can actually say to the system, where there's very little activity occurring around the stress limits, keep the nodes at a large level. However, wherever there's larger stresses occurring, reiterate that even further. So loop it, make the resolution greater. So you could say, if this was 2mm gap between each node, you could say here, make that resolution twice the size, well, twice the minimized size of that. If I go make that resolution 5 times, you make it 5 times smaller, and you end up with something a little bit more like this. And it allows it to be adaptive. Now, because this is a pipe, we don't get a lot of activity that occurs from it. But I'll show you. So if I run that through again, let's see if it gives us any variation of results. It very well might do, because that back end of where that stress was concentrating was on the connecting point to the wall. I don't imagine it will give us very much insight though. Yeah, it's not giving us an awful lot. In fact, in some ways you could argue that it's minimized a little bit more. Yeah, it's still giving us very much the same. We're still in that right ballpark. The initial calculations are correct, but what I'll do is I'm going to come onto my mesh, and I'm going to add some sexy stuff in there to make it even more accurate. So I'm going to go insert. When I go insert, this is the type of stuff. Now, I know some of you have already looked at meshing before with Akinola, but what I'm going to do is not CFD meshing. So I know a lot of people go, well, why don't you just use the inflation meshing? In solid mechanics, it doesn't work as nicely as you'd like it to. Inflation meshing on something like a flow is absolute golden. It's brilliant. But with the solid mechanics side, it's a bit glitchy and a bit of a nightmare, I should say. I can do face meshing. Now, the idea of a face mesh is that I can say to the rest of the system, ignore everything else, let's just concentrate around this particular face, and let's build a mesh around it, and then grow around whatever mesh I've chosen to go onto this face. If I go to method, this is ace, right? So what this will do is it will refine my simulation. The original mesh will do all the refining, and then a method, what that will do is say, right, what I actually want you to do is use this type of mesh and select the best way of doing it. The trouble is hiring computational elements. So when you run it, it could crash. It can be slower. It can be a bit poor in its ability to be quick. So a lot of people do get annoyed. Just because if you're busy at work, if you're busy at whatever job it is that you're at, and if you're hitting a simulation, and some of these simulations can take days, months to run, and if you're using a method, it can double it. So the only reason I'm going to use a method here is so we can actually use it, so I can actually show you this thing in action. Well, I say show you in action, you'll look and go, absolutely nothing's different. But what this will do is try and assist what's going on. So you see here it says, right, geometry specification, and it's saying select your geometry. So I select my geometry, and then I click OK, and then it says what type of method do you want to suppress anything. I'm going to go no. I'm going to do no for no suppression at all. What type of method would you like to use on this geometry? I could go automatic, or I could choose what I want to do. Now I'll show you some of these. Some of these are ace. Swept is a description very similar to any of you CAD savvy people will know, sweeping between two geometry faces. Because it's a pipe, it literally says front, back, sweep, and that's what it will do. But what we'll do is just take a look at all of them. So tetrahedral mesh. So yeah, this is actually going to make the tetrahedrons now. Now when you come back, you kind of look and go, what's it done? Click onto mesh. That is what it's done. Now, please don't follow me on this. I just want to. I'm dying to show you what happens when you do a crap mesh. Now this is awful, but so this will give me some great results to actually show you when you get people who say it's okay, I'm just going to hit default. This is a pipe. Granted, it was very unlucky for me for that, but look at that. It says 53 megapascals. And then you look and go, well, that's 55. And if we did not calculate this, when you look at the simulation, so I'm going to drop the mesh off. Let's say you were going to the boss and you're going in and going, right, that's my mesh, that's my simulation. If the boss doesn't know any better, the boss can sit there and go, yeah, I like that. Yeah, at least it's showing it's not failing. When really all I've done is kind of bullshitted my way through. I'm just gone, yeah, I ran it through simulation, it's got all the right nodes on it, and then what it becomes is quite dangerous. Because let's say, for argument's sake, this is a bracket for a chair. Somebody sits in that chair, it then fails on that chair, then they fall back and they injure themselves quite badly from just falling out of a chair, which is very common. Just because one person wanted to look the bee's knees, it's actually put a lot of people's lives at risk, or health at risk, I should say, which is much more important. So with this, it looks dead straightforward, but it is lethal. Now, luckily in this one, it did the automatic selection, which is a swine. But you can see there that even the deflection is totally wrong, and the stress is totally wrong. But it gives you a result that you could present and go, yeah, this is me, and it's just wrong. So let's get back to this. I'm going to come back to my method. And I'm going to drop this back down, and let's go hex dominant. At least one body. Yeah. It's basically because I'm talking about using hexagons. It's saying you've got a circular pipe. Don't be so stupid. So yeah, it's just ANSYS giving me stick. So I'll bring out the hexagon dominant, and a sweep. Sweep is epic. So you look here. When it says free sweep mesh of quads and triangles, or I could go all triangles or all quads. Let's just leave it at quad and triangle. Update. And this now mixes the two. It's a great tool. So we look now and you kind of go, yeah, but has anything really changed? If you look here, to get the best circular behavior, it's actually put a triangle in there. So what it actually does is it allows us to then use both. Now, as I said, methods are really great, but they are really annoying because they will just suck up all of your computational processing elements. But using a method, I love it. So anybody who's on motorsports, Graham's used methods all the time for different types of things, and it is apologies, I know the bad network quality just came up again. No idea why that's happening, because it's not my internet feed. And then into sweep, and on my method here, just for completion, I can go to multi-zone. Multi-zone we will visit. Now the reason we're going to use multi-zone is you may need to change the mesh as it's running. You may want it to be quad, you may want it to be triangular as it's running. When would you need to do that? When something is moving. If you have two bodies about to hit each other, that mesh needs to be able to adapt to become the best type of mesh. So you can use what's called multi-zones, and it's crazy what it could do. Or you could just leave it on automatic. I'm curious now, if I leave it on automatic, what mesh will it select for me? Because that's what that will do. Come back in, and we come back, and you see there, we've got these triangular structures here, and we've definitely got one there as well. So it's used triangles and quad, exactly what we were looking at. We could just change that to triangles, but we now know, because I showed you what happens when you just use triangles on something where it should be quads. Showed you the result of what you get. So let's get back to something a bit more serious. So come back onto here and let's run it again. So we run back in, back onto the stress, and with 59.7, 1.8, yeah, 59.7, and yeah, you look here, we're still very much at that angle approach. And look down here, so our maximum is 59.7 and we're into 2. Our distance between the two hasn't changed, and what I would like to do then is just, what I should point out is, if anybody's curious, you can spend months developing these, refining them to try and chase that value. But you should always keep in mind, node to element, the method of doing this from the start is ultimately flawed, which is a bit frustrating, but it is ultimately flawed from the start. So all I've done here is, under my mesh, I've changed my spanning angle. So the angle of when it's going to span between things, I've made it a really fine one. I actually don't think that will give much difference. Notice now, because I've gone fine, it's brought in the angles, the distance between them, and now it's going to give me a little bit more of an insight to its behavior. Excuse me. To come back to mesh, 59.8 and 53, yeah. So we're pretty much at that element now, and that's, I mean, the truth of it is, I'd be more than happy to produce a report on this anyway and take this into the boss and actually talk about it. But the most important thing that I did want to show you guys, which by me actually modifying this mesh, I could show you, is the behavior that's coming from it. It is lethal if you just choose a very bog standard. You need something to measure against. If you don't have something to measure against, it can be incredibly tricky and incredibly dangerous to do so. I'm aware of that we're on 25 past 12, so we've still got a little bit of time left yet. So there's a couple of things I'd like to do before we move on. So we've now got this structural steel. We now know through verification it will work. We now know it will do what we're saying it will do. And the story with Marin, they did go back, but they went back with 2 separate materials to tell them the difference in variance. So what I'll do is just close this, and I'm going to bring in that particular material. Let me just find where I am. There we are. Oh, I'm yawning. Right click onto engineering data, edit engineering data, and now what I want to do is I want to bring in aluminium. I don't remember the exact grade, so please forgive me for that, but I don't remember the exact grade for what we were using, what they were using, sorry. But under engineering data up here, I'm going to left click. This now allows me to examine ANSYS's built-in engineering data sets, and they have an awful large amount. You can do an awful lot of good stuff on here. Now, they've only recently brought in the composites materials library. We will be examining composites materials. It will be very tricky. I'm probably going to have to give you the geometry, just because it will be surface modeled. Anybody who's doing my surface modeling module, I'll expect you to make your own. Just saying. When we come to additive manufacturing materials, this is really interesting, so please do not get too excited with this. When it comes to additive manufacturing materials, so your standard steel and the behaviors of that steel densities based on the temperature that it runs at. And I've had a lot of people look on that and go, well, where's ABS, where's PLA? That is a big debated material. There are huge, massive debates on them materials. For anybody who's not too savvy on that topic, polylactic acid, PLA, is lactic acids that have been extracted from fruits, that have been extracted from all different types of sugars. A lot of the time it's sugar cane, and it's extracted from there, and it goes through a particular process for it to become its plasticized material. So it is totally biodegradable. However, that manufacturing process is still heavily scrutinized as to how accurate that can be made. There's also further examination into this material about its ability to oxidize, as if you take standard lactic acid and then you place it into an oxidized room, it will develop to what's called lactic acid bacteria, so become LAB. And there is a quite strong concern from some of the research community of that if you have polylactic acid against human skin, for example, there is enough temperature there to excite the atoms for them to open up to allow for the top surface to become bacterious. This is then further spread to people using graphene, copper, silver, actually in polylactic acid, to kill possibilities of bacteria. So that's one of the main reasons why you don't tend to find PLA in particular on these databases, because nobody wants to put their name down and say, right, that's what it does, just because it's so, the error between it is monstrous between all of them. It's just for your insight. Grantor design samples. So you see how we got Grantor on here. Now, this is Cambridge Materials Selector. For those of you who know Natalie, she will be taking you through quite a bit of Cambridge Materials Selector. With Cambridge Materials Selector, it is an amazing bit of kit, but again, it is only for particular types of things. Again, I will be taking you through this, but you can pull all different types of materials. If you do get a chance and you're bored, I would recommend just going through some of these materials. Some of them you look and go, that is amazing. And the one thing I've always loved about ANSYS, if I drag this out and bring this over to here. Oh, come on, there we go. Look at this. You know, you look at some materials sometimes and you go, nah, where did they get that value from? Don't trust them, go to the reference. They will actually give you the reference of where it's coming from. It is such a useful tool to be able to just look and go, right, I'll go look at that. I'll look at this to tell me exactly what's going on. So it is incredibly useful for stuff like that. If you are interested in building your own material, which everybody wants to, you can build your own library. So if you have custom materials, so just as an example, at the university with the graphene, what they call themselves now, Graphene Engineering Institute or something like that in Manchester, or as they're nicknamed, the Geek. We had some prototype graphene which was infused with a particular type of carbon fiber. This material is bizarre stuff, it really is. So we tested it and tested it and tested it, and I built a prototype graphene library for carbon fiber. So I know how graphene behaves, and it almost behaves non-linear in many ways. But it is true what they say, when it's impregnated into carbon fiber, we can prove that it behaves, in some cases, 10 to 15 times better than steel, which is just bizarre. But I say in some cases, in some physical tests, so it just depends. Anyway, right, I've digressed massively there. So that's the type of thing that you can do there. General materials, this is what we're going to use, just for this, to show you guys what I mean. So, I don't remember the exact aluminium alloy that they used originally, so I'm going to bring in some that I can find here. So, you see here, we've got aluminium alloy. I'm going to use that as my example from what Marin did, well, what ANSYS did for Marin. So I'm going to go to aluminium alloy. See if I've got a star here, left click it once, the book appears. This book says, right, it's in your study. That's what the book's meant to mean. It's used within your study. And then, just for argument's sake, let's look at copper alloy. And what I would like to do in my little note set, what I would like to do is I'd just like to note down the Young's modulus. So I'll say Ca. So copper alloy, Young's modulus, Ca. I've got 1.1 E to the power of 11, and also my aluminium alloy comes in far greater, far less, as we'd imagine. Aluminium alloy L, and this will now come in at 7.1 E E to the power of 10. So we've now got a good insight where we're going with that. I'm just going to come back. The reason I've done that is when we get these studies, the thing is on these lower end FEA softwares, it'll come back and say your part has failed. On this software it won't. It'll just presume that you know what you're looking at. So see how here I've got my engineering data. I'm just going to left click it, and now what you see is we've got 3 variants in the study. So if I go back to my original study, see here where it's got all these weird boxes, it's saying we don't know what's happened, but something's changed. So as I double click it, it's going to say, do you want to update? Yes, of course I do. One thing that annoys me is just everything just can be so slow sometimes. So we're back in, and we've got here. Now, if I look over here, I've got my 3 materials. If I go to solids, what I'll do for the first one is look at what happens when it runs in aluminium alloy. And then run it again. Because don't forget, I could now easily go back to, I say the boss or whoever, I could now go back to the team member and just say, I've already verified this, so I know that my simulation is good, I know that it works to this level of accuracy, I don't need to keep verifying the same material, or else am I not just reinventing the wheel in many ways? So if I come back, go to my stress, oh, we've got 61 megapascals. So it has gone up. It has gone up. But being is 6, so yeah, we're still in a safe behaviour. But often in these types of things, it might not be the stress of it that's a concern. It may be the deflection. Now, don't forget, for the bike example, they were interested in that deflection. I'll have to find the exact deflection amount that they're interested in. They didn't want it to deflect too much because nobody wants to ride a bike where if it hits, it deflects and cripples. So you want it to try and have its own level of rigidity. So if I click onto here, and sorry, 1 second, I'm just going to set my phone to do not disturb. All right. So what you see now is we've gone up drastically. If you look at our original value that we talked about, it's 1.8. We've now gone to 5.1. Almost 5 times bigger than what we're getting. Really, if deflection is not a concern, then fine, aluminium alloy would be alright. But if it is a concern, in this case, it would not be an ideal choice for this type of thing. And again, if I just go back to my solid and then drop this again and add in copper, and then just run it. And this now, because it's all set up, because it's all verified, I can look at all different types of things. I can even look at a variation of the actual material thickness. I could look to see if I could minimize the level of material needed if I'm operating around a particular rule or condition. Now, a student said to me yesterday, or it might have been the day before, could you not just do this with the linker? You know, last week we did the drawing across. Truth of it is you could do that. Now, the only reason I wanted to take you through this first initial stage of doing meshing procedures is it's a nice simple geometry. From this point, I don't want to be using simple geometries anymore. I want to be moving it on to something a bit more industry standard. So our next example that we'll be working on with this will be the ASTM D36, I think it is, which is the push rod standards, so the dog bone samples. We'll be using the standards to verify our results, to make sure that we're getting something correct. Then we'll be going on to it, and then what I'm going to try and do is see if I can get a video of this thing running, and then we can even map it to that as well and get a nice overview of actually building a real industry standard example. So onto my copper. Yeah, now we brought that value down a little bit. It's still obviously nowhere like structural steel, but we brought that value down just a tad, not much. The deflection is much less. I'd never really advise copper for a road bike, but it just starts to introduce the idea of testing for different materials, looking at the types of things that I'm getting, and good question. I had a cracking question. Literally, I just got to read it out because it's a great question. Looking at verifying tubes, how would you verify the aerodynamics profile? So I know what you're saying. You're saying because most profiles on a bike are actually corded. The cord of it. Now, what they will tend to do is they will take the lowest area of that profile. So if you think of your cord, let me just pull out a drawing. Let me just. What they do is they segregate it. I'm just going to see if I can get you a good example of it. It's a good question, so I just wanted to elaborate on this a little bit further. Verifying this is a whole new level of nastiness, but it's a great question. Yeah, so for anybody who's not sure what the question really was, I just want to try and find it. This one's a great one, and I know that there are more specific ones. If you come into there, see how we've got these really corded profiles, we've got these really individual profiles within it. What they'll try and do is they try to segregate, they try to separate the two between, and they'll treat them as two separate sections, very similar to what you would do on an I-beam. If you were calculating out your I-beam, you work your cross sections out and then add them all together, and that's normally how the best that they could do it. However, this does really present back, would you be capturing all that profile? And it's very true. Would you be capturing all that profile? I might actually put a nice bit of I might see if we can do an extra tutorial with that, because I think that's a great question about looking at the cross section of an aero profile. Right. So I apologize, I can't give you a 100% answer with that, but I think I'm going to put an extra shits and giggles tutorial together, just because what I mean is it's not going to be added directly to the notes, but it is a great one to ask for some verification on. Right, so that's the actual profile. That is what I really wanted to cover with you guys. Really wanted to just look at the meshing procedures on it. As I said, from this point we're going to be doing less small geometry pieces like that. I did set a challenge. Now I know some of you have probably seen this come up. This was one that my lecturer originally set up with me. Well, set up with us as a class when we did it, and it was an interesting one. So let me just open this up. I'm just going to bridge this across. Oh, sorry, the question's still on the screen. 2 seconds. So this is the challenge. It's a seatbelt clip. This is, if you, well, I mean, I know they don't look exactly like that anymore. They're a bit more defined. So I've given it a 2.5mm thickness. That is the overall size of it. It is all in millimeters. I noticed yesterday when I uploaded it, didn't put my units on. It's like, wow. But I didn't put my units on, but it is in millimeters. And I picked a really shite material, which is the aluminium 3003 H18, and the test was, with an aluminium alloy of this type, would it survive? So I'm not going to answer that this week. I'm not going to take you through how to solve that this week, but can you check to see if that would be successful if it was used? Now again, where we've got the back plates, let's just keep this as simple as possible because it's just a bit of fun. It's not part of the actual module. I just wanted just a bit extra practice. So the back plate here, we're going to presume that it's held. The force, obviously this clicks into the unit and is restricted around this back plate here. So the force is obviously going to pull this apart, putting the whole actual plate into tension. So the question is, will it survive? Again, anybody who's up for that challenge, please do have a crack at it. Let me know how you get on with it. But do give it a go. Right, so we're on quarter to one. This is what I was going to really cover with you guys this week. I'm going to take this, what I've done here, I will upload this to Teams. I'll zip it all together with my excellent spreadsheet. I mean, really, we could have just used MATLAB. MATLAB would have done it much quicker, but do it with my excellent spreadsheet for my verification spreadsheet. And I think that we've now moved into the three-dimensional space. It's nice that we've moved into the three-dimensional space. What I'd like to do from this point on is move with a bit more traction, let's say. We're going to be a little bit more intense. So next week we are going to move towards that verification dog bone. We're going to look at pulling the dog bone apart. We're going to look at verifying the stress that's traveling through it, the strain that's traveling through it, the deflection that's occurring around it. And then we're going to look at an actual video. If I can find this bloody video, we're going to actually look at a video, and then we're going to try and build a verification model. I mean a validation model, sorry. So what I mean by that is it's a physical test that somebody's done it. We're going to calculate that out to get something right, and then we're going to tie it all in with a nice little simulation just to try and give us that overview of what a full validation model would look like. Then from there, we're going to progress on. We're going to move away from just a single parts from that point on, and we do need to start visiting assemblies, because then we'll have looked at meshing, we'll have looked at verification, and I don't want to spend too much time on just looking at verification. There's more and more tools that you need to know about, so we'll be moving on. So from there, we'll move to meshing. We'll move to assemblies. We'll look at the way assemblies talk to each other. Then we're going to do carbon fibers. We're going to look at multiple layups of carbon fiber. We're going to look at, say, carbon fiber. We're going to do a sandwich to an aluminium honeycomb structure, carbon fiber, a true layup. Then we'll look at the possibility of that layup failing due to delamination, shearing. Then finally, to tie this off nicely, we will look at what's called explicit dynamics. We will put something into motion, and then we will look at the result of the impact of what's happening. And I think then we've got a nice overview of the foundation of what ANSYS is and some of the big things that this system can actually do. So let me stop recording.